Hello, everyone. Welcome to this panel discussion on cutting-edge psychometric and statistical methods in the era of educational big data. So data-driven approaches have taken a big role in supporting informed decision-making at all levels in education. Hence, education researchers and practitioners need to be equipped with proper statistical tools and protocols to navigate the ever-growing noisy data. Often, methods developed in educational measurement and statistics community hardly travel outside due to lack of effective broad dissemination. So in this session, 4 panelists will introduce their developed methodology and tools for wide applications. Specifically, the panel includes 4 projects funded under the Statistical and Research Methodology program with a common focus on developing and promoting proper use of cutting-edge psychometric methods to handle both micro and mesolevel big data. So such data includes fine-grained interactions between learners and their learning environments, such as responses, response times, click streams, and text data that capture learners' social abilities, affective states, or evaluations of teaching effectiveness. So here is a list of 4 presentations by 4 panelists, and each presentation will take about 15 minutes. So each presenter will present one by one. Okay, so Wes, please take over.
Hello, welcome to this presentation on uncovering the hidden complexity in statistical models. While the theme of this panel is focused on analysis of big data, what I'm going to talk about today is fairly general, but I think it certainly applies to the types of big data research questions and problems that we face in the education sciences, particularly because when dealing with complex phenomena that we're trying to understand, researchers in education typically rely on some sort of statistical model to represent the patterns in the data that they have collected. And today I want to talk about complexity and the role or the sort of hidden aspects of complexity that can be sort of embedded in our models in ways that we might not be able to detect using standard methodologies. First, I want to give a definition of complexity. And this definition is taken from Myung, Pitt, and Kim in 2005, and they give a very broad definition of model complexity. They define it as a model's inherent flexibility that enables it to fit a wide range of data patterns. So you'll notice that this definition of complexity doesn't include things that we might typically think of as indicative of complexity, like the number of parameters in a model. This is more general than that. It's just defining complexity as the ability of a model to fit a diverse, wide range of data patterns. So what that means is that complexity might not just be tied to the number of parameters. There might be different sources of complexity in our statistical models. So to introduce these different sources, I want to provide a quick illustration. Suppose that you have collected some data and your observed data is made up of these 7 data points. So just a simple illustration. Now we could model these data with several different, an infinite number of models, just to look at 3 types of models that vary in what we typically think of as complexity. On the left, you see those 7 data points, same exact data, represented by this downward linear trend. Something like a simple linear regression model could be useful to characterize something about the observed data. As X goes up, Y goes down, for example. The middle figure here shows more of a curvilinear function. This captures maybe something more closely related to the data. It does appear to have some sort of curved shape. So that could be a different model that we could fit to the data. And that model would be more complex in ways that we'll discuss shortly. You could continue up this continuum of complexity, and you might arrive at a model that's very flexible, very bendy. And so with a highly complex model, you could actually perfectly fit all of those data points with no residual term. And so these three models differ in complexity, where the one on the left, it might be overly simplistic. It is capturing that downward trend, but there are some points that are far from the line. There are some that are right on the line. The model all the way to the right is too particular to this data set. It's too specific to this data set, and it's probably overfitting the observed data. It might not generalize well to other data patterns. The model in the middle is a compromise between the two. It doesn't fit perfectly, but it's probably better at capturing that trend that exists in the data. So to apply some formulas to these examples, let's suppose that that model on the left is a simple linear regression model. We can model it with y equals b0 plus b1x. We have an intercept term, and we have a slope coefficient, just two parameters. And so we could increase the complexity of this model by adding more parameters. And so we might call that parametric complexity. The figure in the middle, for example, might be obtained by adding a squared term. The figure all the way to the right might be found by adding a higher order polynomial. And so in these other models, we have added parameters, and by adding parameters, we are giving extra flexibility to the model. So it's more complex in that sense. If we were to evaluate the complexity of these alternative models, we might use things that are familiar to us, like AIC and BIC, and we can make these relative fit comparisons and penalize for adding extra parameters and so on. However, it's not just the number of parameters that is a source of complexity. We can increase the complexity while keeping the number of parameters the same. So we might call this configural complexity. By altering the configuration of the parameters in our model, we can change the complexity. So that middle function might be represented by this sort of exponential formula. We still only have a b0 and a b1, two terms that are estimated, two parameters, but this function would be better at fitting data that look like this curvilinear trend than the simple linear regression model would. We could even find a function that has that very flexible model that fits precisely to the data by looking at something like this sinusoidal function. b0 times sine of b1x still only involves two parameters, but the complexity is much greater. And so this configural complexity is what I'm referring to as the hidden complexity. It's not as obvious that a model with the same number of parameters might be more complex than an alternative model that just configures those parameters in a different way. To evaluate the complexity, this sort of hidden complexity, where we have the same number of parameters, we have to use tools that are less familiar to the education sciences, such as the principle of minimum description length. And I'll talk more about that shortly. So because we have these different ways of evaluating complexity, we have different methods of evaluating models, we need to consider the pros and cons of sort of varying perspectives on model evaluation. We have what I'm calling the traditional view. This is sometimes called the frequentist perspective, where we rely on things like goodness of fit testing, or maybe we rely on bootstrapping methods, and we sample from our data, or we do parametric bootstrapping, where we sample from some underlying distribution. However, these familiar methods do not consider the configural complexity of a model. They don't take into consideration that the difference in the configuration of the variables could imbue the model with a higher or lower degree of complexity. An alternative might be to look into the Bayesian perspective, and Bayesian inference provides very useful model evaluation methods, such as predictive model checking techniques. But these also, while they may provide additional insights beyond the traditional methods, they also fail to address configural complexity. It's very hard to detect this hidden complexity with these either traditional or Bayesian approaches that make up essentially all of educational model evaluation methods. An alternative, however, comes from information theory. And within information theory, the model evaluation methods allow us to investigate the configural complexity of a model, the principal minimum description length in particular, gives us insights into properties of a model, regardless of the data that are being fit with that model. So that's a really unique way to approach model evaluation. The key insight of this minimum description length principle is that goodness of fit, as we usually rely on for ascertaining the qualities of our models, this goodness of fit is a composite. It includes the fit to the regularity in the data, the meaningful pattern or trend that we care about, and the fit to the noise that's inherent in the data that we've collected. And so goodness of fit, we shouldn't take on its surface. We need to consider that part of the reason a model fits well is because hopefully it's captured the regularity we care about, but part of the reason that it fits well is because it's captured some noise that we don't care about. And so the two-part minimum description length principle directly addresses this trade-off between goodness of fit and complexity. Just as a very quick introduction, MDL is within the field of information theory, and so it focuses on encoding models as a sequence of bits, of zeros and ones. And so information theory says anything can be encoded as zeros and ones, such as binary data that runs our computers. And we can do the same thing to encode a model. So we could represent it as zeros and ones. The best model, according to MDL, to explain the data is the one that minimizes the total description length, the total number of bits that are needed to describe the regularity and the noise. So the length of the model is the number of bits needed to describe the model. This is the regularity. The length of the data given the model, excuse me, is the number of extra bits that are needed to describe the data after encoding the model. So this is the noise. And this isn't too much different than what we think of as measurement error. We have some model, and then we have deviations from that model that would be representing the exact nuances and specific idiosyncrasies of the data that we've collected. And Vitani and Lee demonstrate that compression of descriptions almost always gives optimal prediction. And so if one of our goals in modeling is to have generalizable models where other researchers can use our same models and fit them to their own data, this minimum description length principle is going to allow us to detect the models, or to select the models, I guess I should say, that are more generalizable. However, MDL is a principle of data compression. It's not something that's easy to implement. Several formulations have been developed. For example, the normalized maximum likelihood is shown in this formula here. And this is just a ratio of the likelihood of the observed data given some model over the likelihood when the model is fit to all possible data in the complete data space. In other words, the normalized maximum likelihood quantifies the information in a model adjusted for that model's propensity to fit well to all possible data, or to any possible data that you could fit into that you could fit with that model. Unfortunately, the denominator you see there has an integration sign. So we have to integrate across the complete data space, which is usually not tractable. But although we can't work with the normalized maximum likelihood directly, we can use that reasoning of the MDL principle to evaluate some models that we are more familiar with in quantitative psychology and education. If we can generate the complete data space through simulation methods, then we can investigate this hidden complexity. We can investigate the tendency of a model to fit well to any possible data. And this isn't a new idea. Cutting it all suggested that people should use, that people could establish a baseline for model fit by fitting their models to many random data sets, and then making sure that the model you choose is doing better than it would relative to random data. Chris Preacher in 2006 used the term fitting propensity to describe a model's ability to fit diverse patterns of data, all else being equal. And that last phrase, there are many things that could be equal. What he focused on is the number of parameters being equal. So he examined the fitting propensities of competing structural equation models that had the same number of parameters, but different structural configurations. He looked at several comparisons of models. One of his examples was to compare the simplex model, shown at the top here, with a factor model, shown at the bottom. And he specified these models so that they both had 11 freely estimated parameters. And then he looked at the RMSR, goodness of fit, statistic to see across all of his 10,000 random correlation matrices that he simulated, random correlation matrices, how often did the simplex model fit well versus the factor model? And you see in this cumulative frequency distribution plot on the right that the factor model was better at fitting data. So same number of parameters, but a different configuration of the variables in that model imbued it with an ability to fit well, to better fit data than did the simplex model. He concluded the good fit of a hypothesized model to observe data, although desirable, can result from the model's inherent ability to predict data patterns and may have little to do with its value as a scientific tool. Cherished models may have to be abandoned or replaced if their past successes can be ascribed more to fitting propensity than to any insight they lend into the process that actually generated the data. In the 2017 paper, myself and Lee Tsai extended Preacher's work to the case of categorical data. We looked at 5 measurement models that are familiar to psychometricians, an exploratory item factor analysis model, a bifactor model, and 2 diagnostic classification models. And we also considered a unidimensional model where each of the items was fit with a 3PL IRT model. The first 4 models had 20 free parameters. The 5th model, the unidimensional model, actually had an extra parameter. It had 21 free parameters because of this 3PL specification that we made. All models were fit to 1,000 data sets and evaluated via the Y2 unadjusted fit index. And we presented the results with this sort of figure here. The square with the dots in it represents the complete data space. And these different sort of blobs that you see, we call this an amoeba plot. These different amoebas represent the area of that complete data space that was occupied by each model. So the black blob represents an exploratory model, and this shows that an exploratory item factor analysis model was able to fit well to 79% of all random data sets that we simulated. And I'm not going to go through all these results. You can find them in the paper. But importantly, the green blob here is a bifactor model. It's a confirmatory bifactor model that researchers would typically attribute to some theory that they have about the relationships that they are trying to measure and the variables and how they're interacting with each other. The green blob is almost as big as the black blob. The bifactor model was able to fit well to 63.5% of the complete data space, to a very large number of random data sets. In other words, the bifactor model is performing almost as well as an exploratory model, and it's very, very successful at fitting data, which is a bad thing because then you can't trust the fit statistics as telling you anything informative. So the results that we found reiterate the importance of configural complexity established by earlier researchers. The exploratory item factor analysis and bifactor models were the most configurally complex. They were able to fit any possible data. The diagnostic classification models had lower fitting propensity, but this is an important aspect of this is that there is a distinct theoretical difference between these models and when they would be used. So they occupy different regions of the data space. The unidimensional model had an additional free parameter. It actually had more parameters, but it was less likely to fit well to any possible data. So it's less complex despite having more parameters. And so this has strong implications for model evaluation that relies strictly on goodness of fit. For models with high fitting propensity, overfitting is a statistical inevitability. For models with low fitting propensity, good fit is unlikely. So it's far more meaningful when you obtain good fit. I know I'm running out of time, just very quickly to talk about the IES award that is related to this work. It's titled Innovative, Translational, and User-Friendly Tools for Comprehensive Statistical Model Evaluation, developed with my co-PI Lee Tsai at UCLA. And our goal is to develop a statistical model evaluation framework that integrates these traditional Bayesian and information theoretic perspectives on model evaluation. One of the major contributions that we're trying to make is to develop a new statistical method for generating the complete data space, for generating the many synthetic data sets that are needed to allow us to investigate the fitting propensity or the model complexity of many types of models. So we're extending our previous work, which was limited in several ways. Now we're going to be able to investigate much longer tests. We're going to be able to look at items with more categories like polytomous data. And we will need to develop we'll need to adapt composite likelihood methods in order to work with this novel data generation method. In addition, we are aiming to develop an R package and a Shiny app that we are calling COSME for Comprehensive Statistical Model Evaluation. And users will be able to specify a model and import data, and then select their preferred evaluation methods. And so they can choose traditional methods or Bayesian methods or information theoretic methods that we've talked about. And then they can export a dynamic report, a report that takes into consideration the model, the data, the types of model evaluation they want to consider. And then they get this multi-perspective analysis of the different properties of their statistical model. And there are some references that you can pause and take note of. And if you have any questions for me, please email me. You see my email there, and follow me on Twitter. Thank you so much.
In this presentation, I will talk about the new sentiment lexicon we developed for student evaluation teaching using text data. This project is also supported by IES. Student evaluation of teaching is a very important topic. The information from student evaluation of teaching can be used in many different settings. For example, administrators have used the teaching report to give promotion to teachers. The teachers can also use the teaching evaluation to improve their teaching. From the student perspectives, the student can also use the teaching evaluation information to decide whether they are going to take a class or not. During the student evaluation teaching, both quantitative and qualitative data have been collected. For example, at Notre Dame, we have a question in the teaching evaluation survey. The question asks how effective a teacher is or an instructor is. So this kind of information is quantitative information. At the same time, we also ask the student to provide written feedback on which perspective of the teaching can be improved for a particular instructor and which aspects should be kept in the future. So this kind of information are qualitative information, and usually it is in the format of text comment. However, the analysis of teaching evaluation data has typically focused on numerical data, but ignored the qualitative data, for example, text information. And we can argue the text information can actually provide more information for teaching. Here's an example. It's a real example from teaching evaluation. From here, we can see using these comments, we have a much better idea about the teaching style and the personality of the instructor. If we only use one value, for example, how effective the teacher is. So we only have numbers. So we don't have all of those contexts regarding the professor or regarding the instructor. Particularly in this comment, the student evaluated the instructor on two different aspects. First, the student's mention of the instructor was very nice. So this is about the instructor's personality. At the same time, the student also pointed out the homework and the exam from this class were very difficult. So that's a different aspect of teaching. So therefore, using these comments, we can see a lot of like more informative like information or feedback regarding this instructor. Actually, this kind of text comments have been collected in teaching evaluation, but we didn't really use that information in our like teaching evaluation, because the bigger question here is how to get the information out from the text comment. Particularly, how do we decide whether a comment is positive or negative, or if in a comment there's different aspects mentioning, how to get those aspects out. And also for each aspect, is the aspect positive or negative? So our research question is to, the purpose of our research is to figure out some ways to determine the sentiment of the text comments in teaching evaluation. Particularly in this presentation, I will introduce a dictionary-based sentiment analysis method. In the dictionary-based sentiment analysis, we use a predefined dictionary to calculate the sentiment of a text. In this dictionary, we would have sentiment expressions as well as a score of each sentiment expression. If we have a text comment, we first identify the sentiment expressions in this text comment based on the dictionary. And then using the sentiment score, we can calculate the overall score of a text. The sentiment analysis has been used like very widely in other areas. For example, particularly in like online comments. But regarding like teaching evaluation, there's no such a dictionary we can use to find the sentiment of the text comments related to teaching. So therefore, in this study, we actually develop a new dictionary that can be used to study the sentiment and aspect sentiment of text comments from student evaluation of teaching. Before I talk about the details, I want to like define some terms. So in a sentiment analysis, we will have sentiment expressions. Sentiment expressions are usually the words or the phrases that express the sentiment of a text. For example, organized and knowledgeable are two sentiment words in this text. And in a text, there might be different like aspects mentioned. For example, in this text, there's two aspects. One is related to the class, another related to the professor. So the class and the professor are aspect expressions. So those are the words that relate to an aspect or describe an aspect. To identify the sentiment expressions for teaching evaluation, we basically analyzed about 11 million text comments related to evaluation. Then we found the most frequently used words in those comments. In total, we found about like 50,000 words that are used at least twice in these 11 million comments. But for some words, even the same words, they can be used as like nouns or can be used as verbs. So if we take into consideration the different formats of words, so in total we have about 94 or 95,000 words. And then we found the words that use the most frequently. So for example, at least they are in the 75 percentiles in all of those words. Then we kept them. And after that, we have about like 20,000 words left in those like expressions among the total of like about 50,000 words. So in addition to use the words directly used in the teaching comments, because there are some other dictionaries that have been developed for other purpose. So we also incorporate some of the words in our word bank to develop our sentiment dictionary. So we actually add about another 1,800 words into those 19,000 words. And after that, we did some menu screening, because some words may not be really related to teaching evaluation, may not be really related to the sentiment of teaching evaluation, but they are frequently used. So we removed those words, and eventually we have about 4,900 words in our list. Next step, we need to figure out the sentiment of those words. For example, whether the word is positive or negative. In order to get the sentiment of the words, what we did is we used the Amazon Turk. So we asked the people to read each of the words in the list we identified earlier. So for each word, we asked them to read from extremely negative to extremely positive. Also for each word, we found 9 to 40 participants to read of those words, which means for example, for a word, so they have an example here. For example, word knowledgeable. I will have about 9 people to read, at least 9 people to read on these words, on this word. Eventually, after we did the survey, we decided to keep about 3,800 sentiment words. The reason is because some words the ratings are very different for different people. For example, the variance of those ratings is very large among the non-participants. We saw maybe those ratings are not very reliable, so we removed those words. So eventually we keep this or not among the words. And then we calculate the average sentiment score for each word. For example, asleep, it has a sentiment score negative 0.22, but for optional is 0.56. We also identify 46 degree words. The degree words used to modify those sentiment score. For example, if you use a total optional, you will multiply this value by 1.5. If it's rather optional, you multiply that by 0.8. Certainly, this is not a very good example. It's optional. Next, we want to identify the aspects related to teaching. So, what kind of aspects the student mention, in their teaching evaluation? So, based on literary review, we actually identify 3 possible aspects: instruct, workload, and relationship. But we want to know which words are related to those 3 aspects. And then we did a survey again on Qualtrics, and we selected 700 comments. And after each, and then asked participants to read different aspects of these comments. For example, we asked them to identify what proportion of the words or the comments are related to instruct, workload, and relationship, and what is the sentiment. And then we asked the participants to identify words related to each of those 3 aspects, so they can basically highlight each word in this text. Now we have a sentiment dictionary. We have the sentiment score, sentiment expression, and the social aspects. So if we have a comments, then we can get the sentiment score for the comments. How to do that? So once we have comment, for example, look like this, we first pass the data into individual words like this. And we also look at the relationship among those words. Okay, so for example, this is not easy. Then we identify the sentiment expressions. For example, easy, love, true sentiment expressions. And then we see how this relates to each aspect, and then we score it. So this gives a table. Basically, we break down the text into individual words. And then we see if it's a centimeter value or not. For example, love is a centimeter expression, and its score is 3.08. And it's also related to which aspect, 1, 2, 3, three different aspects. And we also have the modifiers, so we see like truly can changing like maybe a score to make like a centimeter more positive or less positive. Based on that, we can get a table look like this. So in this case, we have scores for each word based on the centimeter expression and also for the aspects. So the overall centimeter basically add those values together. And for each aspect, we add those values for the expressions related to that aspect together. Okay. So eventually we found like these comments mention 3 different aspects, and those are aspect score, and the overall centimeter is positive. And this is another example. Some texts may not have all 3 aspects. For example, this one only has 2 aspects, so I have the values here. Based on our analysis, we can also identify the keywords related to each aspect. In this case, we can provide some feedback to the instructor automatically. This centimeter score for like real data about like I think it's several millions of data, so we get the centimeter score for each of them. To evaluate the performance of our new centimeter lexicon, so we make some like comparisons. For example, compare our dictionary with other dictionary. And then we also have 2 experts, so basically who look at each of the comments and then decide like the sentiment of the comments, so we calculate the correlation. Notice that like our dictionary has the largest correlation with the expert like information. And more importantly, using our method, we can have more like discrimination like validity. So for example, for the 3 aspects we identified using our dictionary, the correlation among them are relatively low. But if you use the other method, the correlations are rather high. So which means we cannot distinguish those different aspects. So basically in this study, we develop a new centimeter lexicon for student evaluation of teaching. We are, in addition to the overall centimeter, we can also identify the aspect centimeter information. For our next step, we will develop our package. So we will include our like dictionary, so people can directly use the package to get the centimeter score for teaching evaluation data. We'll also like develop some machine learning methods and using this, compare those machine learning methods with our dictionary based method. So finally, I want to thank my students and colleagues for working on this project, certainly the IES funding. And also train for organizing this meeting. And if you have any question, you can email me using the email address.
Hello, everyone. My name is Akihito Kamara from Southern Methodist University. The title of my presentation is Model-Based Approach to Oral Reading Fluency Assessment. I'd like to acknowledge that the research reported here have been supported by 3 IS grants, including the 2 concurrently going on, and also the one in the past. And also I'd like to acknowledge the key collaborators, Joe Neese, Nelly Spotjeter, Yuskara, and Eric Larson. Here's an outline of my presentation. First, I'm going to present the background of the traditional ORF assessment, and also provide the background of the improved ORF assessment. And next, I will present the model-based approach to ORF. And next, I will talk briefly about what is happening on the R package development. And finally, I will talk about what's coming next. All right, and background of the traditional ORF assessment. Well, first of all, ORF assessment is very popular among the education researchers, including the IES projects. So in the traditional ORF assessment, a student is given 1 minute to read as many words as possible in a grade level text, which typically a length of about 250 words. Then a trained assessor follows along and indicates each word of the student reads incorrectly. And after the student is completed, or after 1 minute, the number of the words read correctly per minute, WCPM in short, is reported as a score of the ORF. There are some limitations about the traditional ORF assessment. First, one-to-one test administration is typical, and the manual scoring is also typical, which are the burden for assessors. So as a result, the validity and the reliability of the scoring can be questionable. Second, scores are based on the observed accuracy and the reading time. So the score comparability is hard to ensure. Score comparability is typically relies on the expert judgment of the passage difficulties, and sometimes equating is done, but the typically in traditionally observed score equating is the best we could do. Third, about the measurement error. Measurement error is only available at the sample level, which is only a one number, and no conditional measurement error is available from the traditional approach. Okay, next, I'd like to provide some background about the improved ORF assessment. Okay, first, improved the ORF assessment was developed in the previously funded IS project. In the improved ORF assessment, passage lengths are substantially shorter than the traditional ORF assessment, with the intention to give the multiple passages to students. And the sufficient time will be given to students to complete their readings. And in the improved ORF assessment, the assessment delivery is computer-based. The system audio records students' reading. As a result, accuracy and the time data at the word level can be collected. Next, I'd like to present briefly about the model-based approach to ORF. First, why model-based ORF assessment? First, passages and the ORF scores can be equated by the model parameters, where the common passage non-equivalent group design can be used to collect the data, just like the regular assessment program, which use the IRT. It's very similar idea. Second, standard error. Standard error can be estimated for each model-based ORF scores, unlike the traditional ORF assessment, which is the conditional SEM or CSEM. Okay, how does the ORF psychometric model look like? It is a joint latent factor model comprised of the accuracy model and a speed model. And actually, it is the modification of the van der Linden 2007. accuracy part of the model is a binomial factor model. And the number of the correct responses is modeled as a binomial distribution. And within the binomial distribution, the probability of the correct response for each word is modeled as a function of the passage discrimination and difficulty parameters, as well as a latent accuracy factor score. The speed part of the model is a log normal factor model, just like the Van der Linden in 2007. The speed of the response is modeled as a function of the passage discrimination and the difficulty parameters, as well as a latent speed factor score. And then expected count of the words correctly read and the expected reading time are estimated for a particular reader for a selected set of the passages in the calibrated passage pool. Then ORF score, which is a model-based WCPM scores, and its standard error are estimated. And practically, this is how the model-based ORF application can be done. First, calibration of the data. Calibration data are collected for all passages in a passage pool. Then passage parameters are estimated for all passages. Next, a student takes a selected set of their passages from the passage pool. Then accuracy and the latent speed latent factor scores are estimated. Finally, a model-based WCPM score and its standard error are estimated for any selected set of passages in the passage pool. Next, I will briefly talk about R package development, which is tentatively called ORFR. Our aim is to make the model-based approach to ORF assessment scoring widely available to educational researchers who use ORF scores in their research, including PIs for the IES grants. Some features of the R packages. The package estimates and calibrates passage parameters, and the passage estimates students' model-based WCPM scores and standard errors. So in terms of the estimators, the package have incorporated so far. First, for estimating passage parameters, we have incorporated one Monte Carlo EM algorithm and also Bayesian MCMC algorithm. In terms of the estimating model-based WCPM scores, we have incorporated maximum likelihood, MAP, EAP, and Bayesian MCMC. In terms of the estimating standard errors, we incorporated one analytic method by the Delta method and also Monte Carlo bootstrap method. And what have we done with the R package? We have collected data actually in the previous project on the 150 passages for the second through fourth graders. And we have calibrated all the 150 passages for those 3 grade levels, which means that all the passage parameters for those 150 passages have been equated in the passage pool. And also, we collected in the previous project, we have collected the longitudinal data for approximately 2,000 students for those 3 grade levels up to the 4 measurement occasions. And for each measurement occasions, we have estimated the model-based WCPM scores as well as their standard errors. Next steps. So for the current project to develop the R package, we are finalizing the first beta version of the package, and also the web-based tutorial is being developed. And we are looking for test users of the package, those who have their own ORF data. So if you're interested in the package and if you have your own ORF data, please let me know. In terms of the psychometric model, we are extending the psychometric model to the sentence level data by incorporating dependency between sentences within passage. Actually, this will make the model-based approach more widely applicable beyond the type of the passages that we developed in the previous project. And just additional note, under the another current project, which is under Goal 5, we are developing the tablet applications, which include the automatic speech recognition engine and prosody as part of the fluency measure, and automated model-based scoring for speed, accuracy, and prosody. That's it for my presentation, and thank you for your attention.
So hello, everyone. My name is Chen Wang, and I'm from University of Washington. So today I want to introduce a Shiny app that we've been developing over the past couple of years. It's called VMERG, stands for a variational EM algorithm-based Shiny app for multidimensional IRT applications. So at the beginning, I would like to thank my collaborators, including my co-principal investigator, Dr. Gongjun Xu from University of Michigan, and 3 doctoral students involved on the project, including Jiayin Xiao and Roy Zhu from University of Washington and Tintin Ma from University of Michigan. So without them, the project could not have been progressed thus far. So the general motivation behind developing this app is to help moving measurement research and practice forward. So we know that IES used to have a goal structure, but now it changed to project type. And the measurement projects are always under IES radar, not only because assessment is a key component in instructional cycle, like instruction, assessment, and feedback, but also measurement is usually an essential tool to quantify educational outcomes. So when the constructs that these assessments try to measure become increasingly complex, multidimensional IRT model provides a unified framework and a convenient statistical tool for item analysis, calibration, and scoring. So I'd like to start out by showing an analysis flowchart. So in practice, the analysis of large-scale education data follows several steps, from data collection all the way to making conclusions. So this flowchart, of course, does not include the lengthy process of item writing, which is usually an iterative process by itself. Okay, starting from data collection, if this is a large-scale educational survey data, then the data collection involves complex matrix sampling design. So assume the data is collected from a representative sample. Then the next step is to obtain item parameters, also known as IRT model calibration. So in this step, the best fitting model needs to be decided, and efficient algorithm needs to be used to carry out model calibration. So what Wes discussed at the beginning of this panel, so the methodology he's developing will be very useful for researchers to decide on the best fitting model for their data. And oftentimes, differential item functioning needs to be carefully scrutinized in this step as well. So once the item parameters are ready, then the next step is to estimate either individual students' abilities or average abilities for important subgroups. And after ability estimates are available, then the next step is to make statistical inferences, such as establishing the causal relationship between educational intervention and outcomes. And lots of secondary data analysis are done to establish the linkage here. Eventually, the inferences we draw will guide policymaking decisions that potentially have great societal outcomes. And the vMERGE software that we developed will contribute to item parameter and ability estimates steps highlighted here in red. And let me first talk about the first aim behind developing this app. So while there are many designated IRT software packages available on the market, we intend to develop this app to specifically handle multidimensional IRT models. And multidimensional constructs are becoming more relevant nowadays in educational assessment when people are interested in measuring higher order thinking using computer-assisted delivery. And multidimensional IRT, known as MERGE, therefore provides a powerful tool for enriching the information gained in educational assessment. So for example, like cognitive instructional psychology considers science knowledge and mathematical ability both as highly differentiated theoretical constructs that consist of both basic facts and skills, as well as deeper or higher order understanding. So here is an example from the National Educational Longitudinal Survey in 1988. So an earlier series of dimensionality analysis on this NELS 88 science achievement data reveals that science achievement is multifaceted, and the factor structure can actually change over time. So as shown in this graph, a 4-factor structure first emerged, and then the factor structure appeared to simplify and stabilize in the 10th and 12th grade, likely due to greater curriculum standardization. So we're analyzing the three-wave data longitudinally. Traditional approaches mainly focus on the growth modeling of a unidimensional IRT score, whereas the MERGE approach allows for probing divergent growth on multiple domains, which offers an innovative perspective on construct shift if it exists. So we do observe a gap between research and practice. So in practice, unidimensional IRT model continue to dominate the current practice, for example, in building mandatory state assessment. Although research in psychometrics have provided increasingly sophisticated measurement models. And one reason we think is that when the number of items, sample size, and number of dimensions are all large, the current computational algorithms for MERGE estimation may not be powerful enough to produce results in a reasonable time frame or even ever. Therefore, we propose this family of algorithms called Gaussian variational expectation maximization algorithm, borrowing the idea from machine learning literature that can hugely speed up model estimation. And we hope this vMERGE Shiny app will make the algorithm and models more accessible to broader educational researchers. The second aim behind this vMERGE is to improve the current differential item functioning analysis. So test fairness now more than ever has been a critical issue for any intended test use. And differential item functioning diff analysis refers to the procedures to evaluate whether an item's characteristics differ for different groups of examinees after controlling for overall performance in different groups. So diff is routinely evaluated for any new items added in large-scale assessment as a quality control step. However, the current operational diff methods are insufficient to address the following challenges. For example, it cannot easily handle multidimensional constructs, and it cannot easily take into account sampling weights. And it is designed for two-group comparison. But when the grouping covariate has more than two categories, such as race, then a potential diff-free item has to go through rounds of tedious pairwise comparisons. Instead, a one-step omnibus test is much more efficient to quickly screen those non-diff items. And moreover, in the traditional method, a student has to be assigned to one of the two groups, either reference or focal group. And this treatment may exclude, for example, mixed race students. So instead, we propose this GVEM with covariate approach, GVEM-C, as a new diff screening method that can handle multiple target dimensions and multiple person covariates all at once. And piecing these two aims together, here we show the comparison between the status quo approach on the left and the proposed approach on the right. So here in this graph, the Y's are the observed item responses, and the thetas are the conceptualized latent constructs. So the red dashed line represents the population distribution varied by group. And the blue dashed line represents diff caused by respective grouping variables. Okay, so as shown, so the traditional approaches would analyze each subset of items measuring a unidimensional construct separately, and also treat each grouping variable affecting theta distribution and item responses separately. Instead, we propose an integrated approach that can handle multiple covariates, multiple correlated constructs simultaneously. In addition, due to the efficiency of our algorithm, it can also handle a large number of factors. So for example, here, theta 3 and theta 4 in the graph could refer to cognitive processes such as technical processing or numeric modeling, in addition to content-based factors like algebra or arithmetic proficiency. So here is our envisioned Vimert Shining app modules. So it will handle different types of multidimensional models, including one parameter logistic model, 2PL, 3PL, and also take into account different factor structures. And then it will start out with the exploratory analysis, in particular, the parallel analysis to decide the number of factors. And then it will offer exploratory item factor analysis using either rotation method or the regularization methods to identify the item factor loading structure. And once that is decided, then it will move on to the confirmatory module. And this confirmatory analysis will output both item and person parameter estimates. And we are currently working on producing accurate standard error of item parameter estimates, and that's quite challenging. So we are still trying a few different methods to estimate standard error as accurate as possible. And if external covariates are of interest, then the diff module can be enabled to estimate both item parameters and diff magnitude or simultaneously. So we have recently launched Vimert app 1.0, and I will show a very quick demo of one module at the end. And here is a list of functionalities of Vimert 1.0. Here I provided URLs, so you can just copy and paste these URLs in your web browser so that you can use this software. So in the first step, you can use parallel analysis to identify the number of factors. And then the step 2, we actually separate out the 2PL versus 3PL model because the algorithm itself is very complicated and takes a long time to load on the Shiny app server. So if we lump them all together, it will simply time out because there is a constraint. There is a time limit constraint for uploading backend computations to the Shiny web, and it's 5 minutes. So since the application is so complicated, the algorithm is very lengthy, so we cannot lump them together. So we separate out 2PL versus 3PL models. But under each model, we have both the exploratory and confirmatory modules. the under the hood algorithms are slightly different for 2PL versus 3PL models because the 3PL model is more complicated. So we use the stochastic version to speed up computations. And lastly, we have a diff module. And we use a regularization method, and we are also adding the traditional likelihood ratio test method as an alternative. And here is a little bit algorithmic details under the hood. So for the Gaussian variational EM algorithm, it is super fast for 2PL model. But for 3PL model, it tends to be slow. So we use a stochastic version instead. And the idea of this stochastic version is rather than computing the variational lower bound for every person in the sample, which could be very computationally heavy if the sample size is large, we stochastically optimize the variational approximation in the expectation step. That is, we subsample the data to form a noisy estimate of the variational lower bound and iteratively update the estimate with a decreasing step size. And here, the step size is denoted by the epsilon t+1, assuming this is the t+1's iteration. And epsilon t sub t+1 is defined by this equation here. And this R is the forget rate in the range of 0.5 to 1. In the app, the default value for R is 0.51, but the user can specify any value between 0.5 to 1. But based on our simulation checks, 0.51 seems to work the best. And the tau is the decay rate. So the forget rate controls how quickly the old information is forgotten, and the delay downweight early iterations to decrease the effect of earlier noisy estimates. And in the app, we fixed tau to be 1 because based on our simulation check, that seems to work the best. And if we add covariates, so this is the integrated approach. So this model shows the correct response probability for person I on item J. And if you take a look at the model, the first two components here is just the usual M2PL model, okay? And the additional components shows the effect of covariates on item response. In particular, here, this beta, this X times beta shows the shift in the intercepts due to grouping variable. And therefore, this beta J, if non-zero, implies uniform diff. And similarly, this gamma J denotes the interaction effect between theta and grouping variable on item responses. So if gamma J is non-zero, that indicates a non-uniform diff. And we envision that both gamma and beta will be quite sparse. So only a small portion of the items may exhibit uniform or non-uniform diff. So we use a regularization approach to estimate both item parameters and this sparsity structure of gamma and beta. So only for those items exhibit diff, then their gamma and beta estimates will be non-zero. Otherwise, those values will be shrink to 0. And here are the current facts of the VMERT app. So it may take a little while to load, and that has nothing to do with the algorithm per se, but depends solely on the R-Shining environment. So even though we've purchased the advanced package from the Shining web page, still it only gives us this 8 GB of RAM. So the computation time really hinges on the capacity of this web-based environment. So we are also producing a standalone package. So if the users want to use the package on their local machine, and if their local machine has much better configuration, so it will take less time to complete. And here are some facts. So for a 5-dimensional 2PL model, and 75 items, 2,000 sample size, and both EFA and CFA takes less than 1 minute to complete on the web application. And for the 3-dimensional model, it takes much longer time to finish. And for 45 items and sample size 2,000, it takes around 5.5 minutes to complete. And I have to admit that for the regularization methods, which is used both in the EFA and diff analysis, it takes much longer time because we have to search for the best tuning parameter. So if we have a grid of 10 tuning parameters, that basically means we have to run the EM algorithm 10 times. So of course, it's much more time consuming to run, and we inbuilt an adaptive mechanism for choosing the tuning parameter. And we also build a warning system. So if after 2 rounds of adaptively seeking for the optimal tuning parameter and still it doesn't work, then you will output a warning message telling users that their final results may not be optimal statistically. So here are the 2 references that we have recently published detailing the algorithms. So please feel free to check out if you are interested in knowing more about the algorithms. And next, I want to take 1 minute to just show a brief demo of our current vMERT package. So now let me show you a quick demo of running the vMERT Shiny app for the multidimensional 2PL model. As you can see here, there is EFA module and CFA module. So let's try just the EFA module. And I'm loading a data set, and this is the simulated data set with 75 items and 5 dimensions. And I use the EFA rotation method, and I just click the run button. And this is the progress bar showing how many iterations it ran so far. And you can download the results after it finishes. Either you choose to download the full results, and this will be the R data file, RDS file, or you can download just the item parameters or the covariance matrix estimates, and each of which will be the CSV file. And once everything completes, the results will also be displayed here. And we broke down the results by item parameter estimates, covariance matrix, and Q matrix. And by Q matrix, we mean the item factor loading matrix, and this will be a binary matrix with zeros and ones, and 0 indicate the item doesn't load on the factor, and 1 means otherwise. And in terms of model fit, it will output AIC, BIC, and GIC. So here you should see the parameter results and the covariance matrix, and we simulated the correlations among the factors to be between 0.1 to 0.2. So the results, the parameter recovery is pretty good. And the Q matrix is a binary matrix, and it's a simple structure. So you can see it actually recovers the item factor loading structure pretty accurately. Of course, if we want to compare the results to the truth, there has to be some permutation of dimensions. And in the end, these are the model fit results. And in terms of the method, we have the rotation method, adaptive lasso, and lasso method. Both of these does not involve rotation afterwards or determining a cutoff for the standardized loading. So for the rotation methods, basically, we have to rotate the raw estimated factor loadings and then transform that to standardized factors and compare that to a cutoff, usually is 0.3. And if the standardized factor loading is larger than 0.3, then we consider the item does load on the factor or not otherwise. And that's how we came up with this Q matrix afterwards. But for the regularization method, we don't need this user-defined cutoff. So, and then there is a separate 3PL with the same setup, EFA and CFA. Then we also have a separate module for diff analysis. Okay, so that's the demo here. And we will open this up to the broader audience and also seek their feedback and update our interface to make it as user-friendly as possible. Okay, so that is it. Thank you. Thank you all for joining this discussion session. I know it's a really long day for everybody attending the meeting today, especially on the Eastern time. It's really late in the afternoon. And all of our 4 panelists are here to answer any questions or any discussions you want to engage. You can either unmute yourself to speak out or use the chat function. So put the questions in the chat so that we will answer. So while we were waiting for questions to pop in, actually I have a question for Aki because I happened to attend the machine learning session this afternoon, and there was a app talking about automatically scoring of reading fluency, but they tend to use more of a machine learning approach rather than a psychometric approach. So they tend to just extract features. Of course, they didn't use those deep learning or neural network approach that automatically extract features from speaking, like from people's reading of the paragraph. Instead, they use some predefined features, and then they use some gradient boost algorithm, for instance, to score reading fluency. So how would you think about moving forward, whether there is a potential to combine the machine learning aspect with the traditional psychometric approach in this domain of assessment?
Well, that's a very good question, and actually, yes, I was attending that session.
Yeah.
Yeah, I thought it was a great presentation, and as a matter of fact, not this statistical methodology grant project, but I mentioned that there is another project is going on concurrently under the Goal 5. Actually, Joe Neese is the PI, and I noticed that Joe is attending this Q&A session, so maybe he can speak a little bit more than I can. But actually, we are working on that aspect as well. And then the goal is to combine the what machine learning can do. Well, specifically, we are working on the automated scoring on the prosody, and then integrate that what we are working on this statistical methodology grant on the developing and the enhancing the psychometric models, and then come to the one place hopefully. So yeah. So but what there AMI is working is different from what we are working. So we are not really, in a competition or anything, but in terms of the methodology that they use and we are used, somewhat, similar, not on this methodology grant, but on the Goal 5 grant. But for our effort to do to develop the automated scoring on the prosody, actually we do use the deep learning methodology to extract features. Yes. Joe, if you would like to speak a little bit more, that'd be great. If you're there still.
Yeah, I'm here. No, you did a great job representing the project in that capacity. So yeah, thanks, Aki.
Aki, I think there is a question for you in the chat box. Can existing data audio recorded be reanalyzed using your model-based approach?
Well, no. Our well, again, so I have to separate the two projects here, but this methodology grant project, we are assuming that the data are already coded into the accuracy and the time data. So for the our package that we are developing, assumption is that the data has been already coded from the audio to the time and accuracy data.
Yeah, actually, I had a follow-up question related to that, because you mentioned about accuracy, like it's a binary data after coding. But then you, in the presentation, there is this word correct per minute, sort of as a pretty widely used criteria for reading fluency. So will you translate that sort of a continuous data into a binary data of accuracy, or no?
Oh, I'm sorry. Do you
Is
mean
that-
the
Yeah.
from
So
WCPM to the
Yeah,
binary class, or?
yeah, right. So WCPM is one outcome, but then that outcome, is that used in the psychometric models or not?
No. When I say accuracy, it is the correct or incorrect for each one of the words. And
Oh,
and then psychometric models actually counted the number of the correct responses, and they applied the binomial model.
I see. So then the passage is calibrated based on the difficulty and discrimination. So basically, it's the 2PL model in the background.
That's right. Accuracy part is very similar. Yeah, 2PL look like the binomial factor model. Yeah.
Okay, thanks. So let's see if there are any other questions from the audience.
I have a question to Professor Johnny Zhang. This is Chi Wei. Can you hear me?
Yeah,
Yes.
we can.
Yes, go ahead.
Yeah.
Please.
Yeah, so because I follow your talk just now, and I find it's very interesting. You give the sentiment words, and then you do quite a lot of work and to label them into the database. So my question actually, because there are existing sentiment tools like LIWC or the other tools, whether you want to consider to use them as at the same time, where you will say you will build up this kind of library, because I can remember this kind of library actually is for your current research, but you want to extend it to the other project as well. Where do you have any thoughts in that kind of way?
Currently, we have tried to build a dictionary for education evaluation purpose. The reason we did that is because there's no other dictionary for this purpose. There are several general purpose lexicon available, for customer review, and also the LWCU mentioned. So, but we found particularly for education evaluation, there's no such thing available. So that's the reason we developed the dictionary. We did do some comparison with the existing ones. We found ours can better reflect the information students students' comments on teaching evaluation. And so we are not sure whether this can work better in other situations other than education, but we'll try that in the future. But one thing we plan to try is actually, because we have labeled data, but we didn't apply any machine learning method to the data yet. So we want to compare this sentiment analysis based on a dictionary or based on some machine learning methods based on natural language processing to see whether actually our dictionary can work better than general purpose machine learning methods. Yeah. I hope that answers your question.
Yeah, that is. Thank you so much.
Thank you.
I see a
Very-
question here
yeah.
from Elizabeth in the chat. Elizabeth asks me, am I developing or thinking of developing any new or adapted fit indices based on my research showing that current fit indices may not be preferable for certain functional forms? Thanks for the question, and thanks for attending the talk. I think this probably isn't the most helpful answer, but I think the takeaway that I hope people would have from the work that I've done on these issues is that it's not that individual fit statistics are better or worse for certain functional forms. It's not that you use RMSEA with this model and you use CFI with this type of functional form. It's a bigger issue and more general, which is that goodness of fit, any fit index on its own has limitations. And one of the limitations that I am trying to make people aware of is that there could be hidden complexity in your models that is driving that goodness of fit in a way that a lot of fit indices don't really account for. And so it's less of trying to develop new fit indices and more of just an awareness that goodness of fit has this limitation where your model could have complexity that is harder to detect. And so the other methods that I talked about in my talk, information theory and minimum description length and all of those things allow us to come at the model from a different perspective, not from a better goodness of fit perspective, but from a different angle entirely. And the analogy I like to use, at least for myself, is to think that what we're trying to describe isn't just a picture, it's like a sculpture. And goodness of fit is looking at that sculpture from one angle. If we're at the museum and the sculpture's out in the middle of the room, we can walk around and we can see what the back of the sculpture looks like, or we can look from above, or we can look at it from different angles and then make a more well-informed overall description of that model. We can have a better understanding of what that sculpture looks like by taking this multi-perspective approach. So I hope that sort of addresses that question.
Yes, thanks, Wes. Appreciate it.
Yeah,
I probably didn't word that question the way I had intended, and it looks like I even misspelled it. So I apologize. So I run into this a lot, just fitting any basic model. It doesn't even have to be a complicated latent model where you have model equivalents. I'm thinking of, you have different models that have different model equivalencies, but some of them just make more sense, of course. And so I was just thinking, maybe somewhere in your back pocket, you're thinking of maybe some sort of, I don't know how to say this, a local fit index, or I don't know. As you described the sculpture analogy, I think that's that's a great analogy. And so I was just curious as to whether you were thinking along those lines at all. I loved your graphics, by the way, so thank you.
Oh, well, thank you. Yeah, there is literature on local fit indices, especially in the sort of causal inference and graph theory literature that I think probably is very useful. I'm not very knowledgeable on those topics. There is a lot of stuff that information theory has to offer that the education sciences do not take advantage of. And there are a bunch of model evaluation methods within information theory that I think could be very helpful to people. There's a whole literature out there that I think is alien to education for whatever reason. Maybe it's too complicated, needs to be made more accessible. I think people need to bridge that gap, and then we'll be able to answer some of those questions.
Okay, thank you.
Thank you.
Chen, you had a great presentation as well. Thank you.
Oh, thanks, Liz. And actually, I want to follow up on Liz's question to Wes, because in the regularization methods I use, I need to use sort of like information criteria to pick the best tuning parameter. That is also a way to balance the model fit versus model parsimony. Mm-hmm. But I know in many of my research, I feel like BIC or even generalized information criteria sometimes cannot pick the best tuning parameter, even though when I look at a solution path, the correct model is on the path, but the information criteria just cannot pick the right tuning parameter. So in that case, do you think this information theoretical approach that you propose could be used to pick the best tuning parameter in the regularization of modeling approach?
Yeah, I hadn't considered that as an application of this stuff, but certainly, BIC is accounting for complexity by counting numbers. I mean, by counting the number of parameters. And so the model with more parameters, it's penalizing it just by counting parameters. There are cases, as I showed in the talk, where competing models can have the same number of parameters. And feasibly, I haven't actually done this analysis, but feasibly you could get very similar BIC results, even with these models that have the same number of parameters, in a way that you don't actually know which one is more parsimonious or more simple or more complex. And so maybe different criteria would allow you to ascertain the best tuning parameters or better tuning parameters, maybe because of that issue. I haven't really considered that, but let's talk about it. Let's figure it out.
Yeah, sounds quite interesting. All right, I think our time is up, and I don't want to keep people here for too long, as it's pretty late on the East Coast. So thank you all for joining the discussion. And if you have any questions to our presentation or our projects, feel free to reach out to each panelist. And have a great night.